Bismillahirrahmanirrahim. Previously, we had talked about the parent quadratic function, this one right here. We made a table like this. I picked some x values, 1, 2, 3, and -1, -2, -3, and we found out the corresponding function values, or f of x values, such as f of 0 equals to 0 squared, and that was just 0, and f of -1, for example, was -1 squared, that's 1. And from this, we had generated this table, and then we plotted these points out. This was 0, 0, and this was 1, 1, and this was 2, 4, for example. And the graph this produced was a graph of this function, this parent quadratic function. And we have said that this is a parabola. And this point here, this turning point, if you recall, we'd call that the vertex. The vertex, or V, it had an ordered pair. In this case, this was 0, 0, and we had labeled that Vx and Vy. In other words, in this case, Vx was 0 and Vy was also 0. The x-coordinate of the vertex and the y-coordinate of the vertex, they were both 0. And we had also made an observation that the graph of the parabola is symmetrical. In fact, there's this line here, and we had called this the line or axis of symmetry. And this half of the graph was symmetrical to this half of the graph, or they were mirror images. Said another way, half the graph was in this side and half the graph was in this side. So the graph of parabola is a symmetrical graph. Each arm of the parabola is a reflection of the other. Now this property, the fact that the graph is symmetrical, is very useful because you really need only to generate one side of the graph. The other side is basically a mirror image of the other side. In fact, when I was graphing this, I plotted this point, and then I realized this point was like 2 units away from the axis of symmetry, so I went only 2 units away to get this point over here. And similarly over here, I graphed this point over here, which was 3, 9, and I realized that this point was 3 units away from the axis of symmetry, so I just went 3 units over here this way to get that point. In other words, to get this point over here, I didn't go to -3 and up 9 like this. I just took this point and reflected it across the y-axis. And speaking about the axes, here I didn't label the axes yet to suggest to you a point. Always label the axes. So this is the x-axis, and this would be the y-axis if there was a y. So you can say this is the y-axis, but in here we're using f of x, so this is the f of x axis. See, the axis is whatever you label it to be. Sometimes the x-axis could be like hours somebody had worked, and this y-axis, the vertical axis, could be their pay. Or a scientist might be studying temperature, and that would be the x-axis over here, and on the y-axis they'll be studying the precipitation depending on the temperature. So x and y-axis represent whatever you're studying. In this particular example, in fact, we're not studying x and y, we're studying x and f of x. So the proper name for this axis is f of x. Now, if you had labeled this axis y, a generous teacher would probably wouldn't mind. Okay, so this is the parent function. So I've drawn the parent function here. Thereafter we said, okay, if that's the parent function, what does this look like? -x squared. In other words, what does the introduction of this negative sign do to the graph? Now, if you recall, we had plotted this out, and the graph of y equals -x squared was a reflection, or like a flip of the parent function. Now this is called the reflection of the graph about the x-axis. So this would be a reflection about x-axis. Okay, so if this was the parent function, y equals -x squared was a reflection of the function about the x-axis. Then we have explored this function. Now, if this is the graph of f of x, what did the graph of g of x, which is 3x squared, look like? What does this 3 do to this graph? And if you recall, this graph basically went up faster. It was skinnier, so to speak. For any given value, it went up faster. Now, the official terminology for this is called stretching the graph. Now, how's that stretching, you say? Well, if you can imagine the parent quadratic function to be like this, and pretend that's like pinned down over here like this, and then if you were to take the vertex and like stretch it like this, the graph would appear to get skinnier, right? Like kind of like this. So that's how you can kind of imagine it. So when the graph gets skinnier like this, it's kind of like stretching the graph. then we had studied another function. Let's call this k of x. K of x equals 1 over 4 x squared. Now this graph, it'll be like chubby, right? It'll go up slow or something like this, right? Now this is called shrinking the graph. Now how's that, you say? Well, again, if this is the parent function over here like this, and if you were to like pin the parent function down over here, and if you were to take the vertex and kind of like push it in there, like shrink it, it would kind of be like this, right? Kind of squeezing it in. So making a graph skinnier is kind of like stretching it, and making a graph like chubbier is kind of like shrinking it. Okay, so the graph of y equals negative x squared was a reflection about the x-axis. The graph of g of x equals 3x squared was like a skinnier graph or went up faster, and that's called a stretch of the graph, like a vertical stretch of the graph. And the graph of k of x over here, which is 1/4 of x squared, is a chubbier graph because it goes up slower, and that's called a shrink. And finally, we had examined the following function, y equals x squared plus 3. Now, if you recall, the addition of this 3 basically moved the whole graph up, kind of like a chess piece across the board. So what I did over here, basically, I took this point over here and moved it up 3 units, and I counted this point over here. It's okay, 1, 2, 3. I moved it up 3 units, and I took this point over here, basically counted 3 boxes, moved it up 3 units like this, and I took this point, moved it up 3 units, and this point, and like this. So I moved every single point up 3 units. And I got this graph, y equals x squared plus 3. Now moving a graph up and down like this is called vertical translation. And if we had said y equals x squared minus 3, basically we would have taken the same graph and moved it down 3 units. So the vertex would have become right there. And the whole graph would become like this. Something like this. So this is called vertical translation, moving the graph up and down. Now, if we were to move the graphs this way, horizontally, like if we were to take this graph and move it kind of like this, for example, this would be called a horizontal translation. Okay, so what I wanted to do today is to develop kind of official language or vocabulary for some of the things that we did before. I would request you to make the following terms kind of part of your vocabulary when you're talking about functions. The term reflection, it's kind of like mirror imaging the graph across either x-axis or y-axis. And the term stretching and shrinking, that is a stretch of a graph or a shrink of a graph. Undoubtedly, it's more important to understand what happens to a function when you introduce a constant like this, a 3 before the x squared and 1/4 before the x squared. One will make the graph go up faster, and the other one will make the graph go slower. Perhaps a more appropriate terminology would be a faster rise and a slower rise. A stretch is a faster rise, a shrink is a slower rise. And finally, we talked about the terms vertical and horizontal translation. That is, moving the graph up and down, that's vertical, and sideways like this, or horizontal translations. So I would request you to make these terms part of your vocabulary when you're talking about functions. Reflection, stretch or shrink, vertical and horizontal translations. The last thing I want to talk about is this concept. Now you realize that there are 2 types of these parabolas. Some that look like U, and others that kind of look like N over here like this. And this depends on this negative sign right there, right? Now what I've done over here, I've labeled the 2 vertices. And every vertex, as you know, has an ordered pair that corresponds to it, just like every point on the graph. Now for this parabola over here, the vertex represents the lowest value of the function, because the function does not go beyond that point. At the vertex, it turns. So this y value of the function, that's called the lowest point of the function, or the minimum value of the function. And this point, that's like the height of the function, this y value, or the value of the function at that point, that's called the maximum value of the function. In other words, in this case, the maximum value of the function is the vy, and here, the minimum value of the function here is the vy. So this terminology, minimum value of a function and maximum value of the function, should also become part of your vocabulary. I hope you enjoyed. Until next time, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.